Okay, let's get started. So I extend the deadline of the homework to 16. I don't know whether you'll notice that or not. Yeah, because we don't have a new homework yet, so yeah, probably you can spend more time on it. But if you need another extension, just let me know. Okay, so I didn't upload the solution yet, but I will do that very soon, either today or tomorrow. Okay. Okay, let's review what we covered in our last lecture. So in our last lecture, we start talking about the channel capacity. In particular, we talk about channel modeling, and then we start introducing about the channel codes and channel capacity. Okay, and here's the channel modeling. So basically, we model the channel as a conditional probability distribution, right? Where X is a message that is a message that we want to transmit, and Y is basically what we received, right? And then we define what is a discrete memoryless channel, and it is defined as follows. So we have a source, we have a input alphabet, and we have output alphabet, and then we have a channel distribution here, right? And the key thing here is that so we need to consider like a block kind of transmission, right? So consider n input source symbol altogether. Okay, so in practice, the channel can be dependent on each other, right, over time, right? So that's why we do this modeling. But however, here we consider a discrete memoryless channel or DMC, right? So the definition of DMC is as follows, right? So basically, the conditional distribution of the transition probability of a channel is given by the individual product of the product of individuals of the conditional distribution, right? And this basically means the channel, the current input does not depend on, the current output does not depend on the past input. Okay, so it's memoryless. All right, and then you may connect this to the discrete memoryless source, right? So basically, the concept is very similar. One is talk about the channel, and the other one talk about the source, right? But what we emphasize here is that for DMS, so it is a mathematical abstraction, right? So basically, the reason we do that is that it's easier for our analysis. Okay. However, here for DMC, so it is also easier for our analysis for sure, but we also use that for, this is also kind of practical, right? In practice, for example, like the AWGN channel, we mentioned a little bit, and we discussed significantly a lot in the communication class. Okay, so we prove that AWGN is actually an IID channel, a memoryless channel, okay? It's actually a practical assumption, right? It's not like only for mathematical abstraction. All right, and the example are BSC, binary symmetric channel, and binary erasure channel, okay? I will give these two examples. And then we define we did not define the channel capacity yet, but we defined the four things here, right? So basically, so this fourth thing will consist of a channel code, okay? And the channel code, normally here we consider a block channel code, right? Again, similar to the source coding. So block channel code is not the only kind of coding we can use in practice, right? The reason we use block code here is that it's way easier to analyze. And later on, we're going to see that block code does not lose any general reality, right? So this actually, we can use this code to achieve the channel capacity actually. And then, so for this code, we have a message set denoted by n, right? And the indices of the messages from 1 to 2 power of nr, right? And r is basically the rate of the channel code, okay? And the code of the channel is given by this. So basically, we have 2 power nr code here, right? And so any code is a block of n symbols, right? So here, basically, what we have, we can consider that as a matrix, big matrix, right? So it has 2 power nr rows and n columns, okay? And n, so every row is basically a channel code, okay? An encoding function is to map the indices from here to the code word here, okay? So this is the encoding function. We use f to denote that. And for the decoding function is to map yn back to the message indices, okay? And then we'll have estimate of m, right? Clearly, we want m hat and m to be equal, right? But if they're not equal, then there will be in error, right? We're going to see some definition of the error today. And the example of the channel code here is the repetition code, right? So that's one of the most simplest a simple code that we can ever imagine, right? So basically what it does is that we map 0 to 0, 0, 0, and 1 to 1, 1, 1, right? So this is a coding, okay? So you can see that it's a mapping, right? So this is an encoding function, right? And for the decoding function, so we can design a very simple decoding function, which means that we can have a kind of majority kind of decoding, right? If we receive more zeros than ones, then we say, okay, it's transmitted 0. If we receive more ones than zeros, then we say it's transmit a 1, okay? So is that optimal? Yeah, we didn't show that yet, right? But it's kind of a meaningful decoding scheme, right? And we compute the error probability in class, and we show that actually using the repetition code, we can achieve a way better error probability, okay, compared to without any channel code, right? So you can see that it's kind of working, but the drawback here is that, so instead of transmit one symbol, we transmit 3 symbols, right? So we can see we kind of lose efficiency here, right? Okay, so yeah, let's see what we're going to cover today. Today, we're going to continue talking about channel capacity. And then we'll give some examples of how to compute the channel capacity, right? It's kind of application of the channel capacity. And then in the very last part, then we're going to show the channel capacity mathematically, right? It's kind of pure mathematical proof, but we're going to talk about the computation and application first here. All right, so yeah, let's give some, so in order to talk about channel capacity, so we need to know what is the error probability, right? So let's define the error probability. So we're going to define a few kinds of error probability here. So the first one is the individual message probability of error. Okay, so definition of that is very simple, right? The probability of error basically means that when m is transmitted, then what is the probability that m hat and m are not equal, right? So that's basically the error probability for the individual message. Okay, so the conditional probability of error given that message m is transmitted, yeah, is this one. So we call that PEM, right? So that's a conditional probability where it's given xn equals to xm, and then then the probability that g of yn, so this equals to m hat, right? And the m are not equal. Okay, so that's basically the probability of error for individual message. Okay, and then so you can see that's a function of m, right? So we have f such kind of metric, right? So we don't want that. So basically what we want is that we can kind of combine all the m together, right? So one way to do that is to compute the maximum, right? The maximum error probability. And the other way to do that is to compute the average of all of them, right? So 2 ways to do that. So the first way is the maximum probability of error. Right, definition of that is as follows. So basically, it's denoted by PE max of C, so which is a channel code here. So it's a maximum over all the message, and then we take PE here. Okay, so the maximum of the error. Okay, and then you can see that eventually probably this is more strict. Yeah, so yeah, let's see that later. So we need to introduce another one. So which is the average error probability. Okay, average probability of error. Okay, so the average probability of error is denoted by P bar of the code. So that is computed as the average of all the individual error probability. Okay, so that equals 2 power nr and this. Okay, and you can see that, so we have an average error probability of error and we have a maximum probability of error, right? So which one you think is more strict than another?
Max is more strict.
Yeah, maximum more strict. Basically means that if it's the average is less than epsilon, we cannot, it cannot imply that the maximum is less than epsilon, right? So later in our capacity definition, so we'll let this guy go to infinity, right? To make sure every individual error is small. Okay, so there's no a big error anyway. Okay, great. And so this is a probability error, and given the probability error, then we can get definition of the achievable rate, right? So we introduce a rate r here, right? So basically we say r equals the log of m, right? But but that is not the achievable rate, right? So the definition of the achievable rate, this rate can be anything, right? You can do whatever you want, right? But what is important is that you need to make sure that the error has to be very small, okay? And for such kind of rate, it's called the achievable rate. It's like the source coding, right? So we say the achievable rate for source coding is that the decoding error has to be very small, right? It has to go to 0 when n goes to infinity, right? Same thing here, okay? So basically, the achievable rate is defined as follows. A rate r is said to be achievable if, again, so here we're considering a block code, right? Then what we need here is a sequence of code with different lengths, right? Like what we introduced for the source coding, right? So this is the kind of information theoretic language that we need to learn. Okay, there exists a sequence of Rn code. Okay, so we use this notation to denote the sequence of the code. Okay, with probability of error PE max Cn, so that goes to 0 as n goes to 0. Okay, so this is called achievable rate, right? Eventually, so as n goes to infinity, then the error will become 0. Okay, great. Yeah, any questions? Okay, so this is achievable rate, right? Then we need to see, okay, what is the capacity of the channel, right? So basically, the achievable rate tells you how many number of bits you can transmit, or how many number of whatever, if it's binary, then we call that bit. If it's not binary, then there's something else, right? So this basically means how much information we can transmit over the channel without any error, right? So we don't know that is possible yet or not, right? As we mentioned in our last class, before channel, what people believe is that 0 error is not possible, right? Because the random channel, we need to have error anyway, no matter what you do. But channel told us that, okay, if we play a trick there, we do a block coding, we code things together as a length n. When n becomes very large, then eventually we can get a 0 error. Okay, so this is what channel told us. Okay, because of this, so then we need to, so the definition of the channel capacity so Yeah, because we can achieve zero error anyway as n becomes large, right? So then the channel capacity has nothing to do, I mean, if n goes to infinity, it has nothing to do with the error, right? So remember here, so now we have like a few quantities here, right? We have channel capacity, we have error probability, and we have block length n, right? There's, there are like more than two, variables here, right? Then, so basically, how we define the channel capacity is basically the maximum number of bits or number of symbols that we can transmit over the channel. Does that make sense? Right? Because we know the capacity is non-zero, right? This is what Shannon told us, right? We don't know why that is true, but let's accept that the channel capacity is not zero. When the error goes to zero, when the error goes to zero, we can still transmit, right? Then there will exist a lot of coding scheme, to have a meaningful R here or non-zero R here, right? So the channel capacity is defined as the maximum over all the R, or the supremum over all the R. Does that make sense? The highest one. Okay, so the channel capacity is the supremum of all achievable rate, or so we say C. The capacity is denoted by C, so that equals the sup of R such that R is achievable, right? Then we need to understand what is achievable, right? So this is the definition before. Achievable basically means that when n goes to infinity, the error has to go to zero. Okay, for such R. Okay. Any questions? So if you compare this for the rate of the source coding, you can see they are like very symmetric. Okay, we have a very similar definition for the source coding, right? The source coding difference here is that we have an inf here, right? Because in the source coding, it's a compression problem. We want the minimum number of bits to represent a source, right? But for channel coding, then we want the maximum, right? We want to transmit as much as possible, right? So the highest number we can transmit for one use of the channel. Okay, let's see an example here. So it's called noisy typewriter. Okay, so now let's see a simple case. Let's see how we can get the channel capacity here, right? The noisy typewriter basically means that when we type something, there's a chance that we can get what we type, right? But it is possible to get another one. It's called noisy typewriter. Okay. By the way, did you know there's I don't know what is it called in World War II, in the very beginning. So in the German, they have a kind of encryptor, encrypt.
Enigma,
What's it called?
Wasn't it Enigma?
Enigma. I forgot. I think what the Polish invent, to decrypt that is called a bomb or whatever. Yeah, you know the history?
Yeah, it was Alan Turing, right?
Yeah. Oh no, it's before Alan Turing. Yeah, it is the same thing. But Alan Turing got the insight from some Polish mathematician. Although Poland lost very quickly, but they have their revenge. The Polish invent this decrypt machine, right, and give it free to UK, and then they get a hint from that, and then invent another even more powerful. The reason Poland didn't kind of build the very powerful machine is that they don't have the money to do so. But anyway, the reason I mentioned that is kind of interesting. So that is not noisy typewriter, but it's kind of, they have an algorithm there, right? When they type something, and then some other things will show up. But there's a trick there. It's very funny. If you type A, then everything else can show up but A, right? Then it's kind of stupid, right? You should have some probability A showed up as well. So, and Turing kind of used this kind of thing to, break it somehow. Yeah, anyway, so for the noise typewriter, so basically when we type something, A could appear, there's also some chance B appear. Okay, if type B, right, B could appear and then C could appear as well. And then if type C, the same thing happen here. And D, and if we type D, right, and E could appear. And if we type E, so F will appear, right? If type F, something magic happen, right? F could appear, and then it will become a closed loop. So A could appear, right? For example, right? So this is called, what happened? This is called noisy typewriter, okay? So now let's see, okay, so this is our channel, okay? And can you tell me how can you design your channel code to make it error-free? Right? If you want to transmit, you're using, let's say, only from A to F, right? So when you want to, when you want to transmit, some information, let's say 0, 1 or whatever, use this kind of channel, okay? How can you guarantee it is error-free? Can you design a scheme there? A simple scheme. Doesn't have to be block code. Or you can, of course. Right? Let's see whether this kind of thing can work or not, right? So basically, let's say if we transmit A and transmit B, right, then there's some confusion, right? Because if we transmit A, we can receive a B. If we can transmit B, if we transmit B, then we can receive B as well, right? There'll be some confusion. But if we transmit A, and then we transmit C, that's it. So will there be a confusion? No, right? Because if we transmit A, we receive A and B, A or B, right? If we transmit C, we receive C or D, right? If you see a A or B, you know it is A. If you see a C or D, you know it is D, right? Similarly, we can also transmit a E here, right? So if we transmit A, C, E, will there be any confusion? Yes.
Well, I'm a little confused. If we send an A and we receive an A or B, we don't know that it's A. It could be A or B, couldn't it?
Oh, let's say we do not transmit B at all. Yeah, we only use A.
Oh, so our alphabet is only A, C, E.
Yeah, you can think in this way.
Okay.
Or, we don't need to think, this kind of we can use this kind of thing like a channel code, right? For example, it doesn't have to be what we transmit, right? Let's say we want to transmit 0 and 2. Okay, 0 means A, 1 means C, 2 means E, something like that, right? So this is the coding alphabet, right? So let's say if we transmit A, C, E, use that 3 as a code word. So will there be any confusion? No, right? And then we can transmit that with totally 0 error. Okay, 0 error is totally possible. Of course, the channel is very simple, right? In practice, it will not be that simple, right? So this is just give you an example that we can actually transmit, at least for this channel, we can transmit log 2, 3 bits per channel use without error. Okay, let me write it better. Channel use. Okay, so this is very important. So per channel use basically means that we use the channel once. Okay, so every time we use the channel once, we can convey 1 out of the 3 symbols, right? Therefore, we have log 2, 3 bits. Okay, so that's how we transmit for this. Okay, but we didn't show that channel capacity yet, right? Just the feasible rate. Okay, so yeah, let's see. Let's get some idea from here, right? So basically, so when we transmit A, right, and for the received symbol, it could be either A or B, right? So the idea why this is working is that the received alphabets are disjoint, right? When A is transmitted, we receive A and B. When C transmits C and D, E transmits, we receive E and F, right? They are totally disjoint. That's why we can decode it without any error, okay? But in practice, it will be never like that. So if you transmit A, everything should be possible, with different probability maybe. But if you transmit A, there's some chance we receive A, B, C, D, E, F, right? So if that happens, can we still do that? Right? Can we still do similar to this if everything is possible? Let's say if A becomes A, B, C, D, E, F with equal probability, would that be still possible. Right? So let's see whether this argument makes sense or not, right? Let's say this is our code. This is our code book. Okay, so our code book is xn. Okay, and when we transmit that, we're going to receive a yn. Okay, so this is our received code book. Okay, and our code word is inside, right? So every point here represents a code word, for example. Okay, great. And when we receive some symbol yn here, okay? So we have a concept called typical set. Hopefully you still remember it, right? So what is a typical set? Right? Typical set only makes sense when n is large, right? So when n is large, we can see that the probability will concentrate, okay? So it means that with very high probability, close to 1, so this would be, what we receive, okay? So this is a typical set. Okay, and denoted by, if we use epsilon, I mean this entropy typical set, it will be given by this, okay? So with very small chance, you'll receive something here, right? Although, everything is possible, but it will concentrate, right? So those are the code words that you're going to receive, okay? So now let's see. Let's focus on particular transmitted symbol here, right? So if, let's say, we transmit this symbol, let's say we transmit, where is it? Let's say we transmit this symbol. Okay. Yeah, that's fixed. Okay. And then, via the channel will follow some probability distribution, right? And what we're going to receive here is actually not everywhere here, right? So what we're going to receive here would be concentrated as well. Okay. So basically, we'll transmit here, and our received message will, with high probability, will in this circle, right? There will be lots of code word here, but not code word, lots of point here, right? But most likely, so here is what we're going to receive, right? What is that? So it's another typical set, right? So this is a typical set of a epsilon n y given x. Bar, okay. So this is given a code word, and then we count, the y here, right? So this is a typical set, okay. And because we have a condition here, so the size of this typical set can be much smaller than the total thing, right? And for this code, for the second code word, so we're going to have pretty much the same thing here, right? So received thing will within this typical set. And for the third code word, for example, right, it could be also like this. Okay, so everything will be in the typical set. Okay, so now I think it becomes relatively clear, right? So can you tell me what is the total size of this typical set, roughly speaking? The cardinality of it. Say it.
2 to the n and then times.
Very good, right? So this is a typical set of here, right? Just y distribution, right? So I'll tell you this. So basically, the size of this typical set, similarly, is 2 power n y given x. Okay. Okay, so now, so what is channel capacity here? So intuitively, so basically, so this small circle is, this circle is almost everything we can receive, right? And for one single code word, it will become this typical set, right? So if we use this area or the cardinality of the typical set divided by the cardinality of this typical set, and then so that will be the total number of code word we can have. Do you agree? right? So basically, this is total number of symbols in a typical set, right? Divided by, so this is the total number of points in one conditional typical set, right? So if you use that, then what you get is the number of code word you can have. So basically, that's your channel capacity, okay? So this equals to 2 power of hy minus hy given x, right? And can you tell me what is hy given x? Hy minus hy given x?
Mutual information.
Very good, mutual information. Right, then equals 2 power n of mutual information. Mutual information between x and y. Okay, so now the rate, so this is basically the total number of symbols you can transmit without any error, right? The rate, or we say c, here is basically log 2 of this guy, right? So this is the total number of bits, for example, right? That equals to the mutual information between x and y, right? So basically, mutual information is your channel capacity. Does that make sense? Okay, so this is intuitive explanation, right? Later on, it's not a proof. Okay, it just helps you to understand why it is true. Okay, so to prove it, we need something else. Of course, the argument will still be the typicality and stuff, right? But it's more complicated than this. Yes?
So what stops the conditional typical sets from overlapping with each other? Especially like you had said, if like it could be any other symbol with equal probability, then wouldn't they all just fall into the same conditional typical
That's
set?
perfect. Yeah, that's a very good question. They cannot. Yeah, I can show it. Yeah, so that's why I say it's not a mathematical proof. It's just intuitive explanation. Okay, later on we're going to show that they will not overlap. Right, or the probability of overlapping is very small. Right, so basically, let's keep it there. So, okay, we're going to show that in the very end of this chapter. Very good question. Yeah, we need to think about that. Okay, great. Okay, so yeah, let's introduce the channel capacity, right? And so one thing to remember here is that for this xn, so that's not the source message, right? Source message is n, right? So this is the coding, the source code. So basically it means that we can design it, right? It's not given by nature, right? We can design it. So basically you can see, so for this guy, for the mutual information, right, it's a function of the probability of x. Right? So if we can design it, then we can maximize it over the PMF of x. Right? So basically, the channel capacity is defined by the maximum of the mutual information. Right? And then the maximum is over the distribution of x. Okay? I have a theorem. So this is called channel coding theorem, or channel second coding theorem. Hopefully you still remember the first coding theorem with the source coding, right? So the maximum compression you can get is the entropy, right? So, but the channel coding theorem means that the capacity of the DMC, discrete memories channel, x p y given x y is given by, so c equals to the maximum over px, the mutual information between y and x. Okay, so this is the channel capacity, and we're going to prove that later. So we're going to see some property of it and how to evaluate that in practice. Okay, how to compute it. Okay, so let's see the first example. Capacity of BSC, right? So that's the simplest channel we introduced, the binary symmetric channel. Okay, so yeah, one observation here is that, so hopefully you still remember what is the binary symmetric channel, right? So basically, it's given by this. Right, so this is a binary symmetric channel, right? So let's say, so one thing we can model this, one way we can model this is as follows. So a BSC can be defined by y equals to x XOR z, right? So this is either XOR or a plus in the binary field. Okay, meaning 1 plus 1 equals to 0. Okay, the input and output both are 0 and 1s. Okay, where x and y are both in 0 and 1. Okay, and this addition is modulo 2. Okay, and we can assume here z will follow a Bernoulli distribution, Bernoulli P distribution. Okay, and of course, this P will determine this epsilon here. Okay, and this is a BSC, right? Then let's compute the channel capacity. C equals the maximum over Px of the mutual information, right? So now let's see how we can compute this mutual information, right? So there are like two ways to compute it, right? Because mutual information equals to entropy of y minus hy given x, or entropy of x minus hx given y, right? So you can do whatever you want, right? But here, so normally one way is easier than the other way. So we use both of them in practice. So here, let's say if we can do this, hy minus hy given x, right? So if we do this, let's see how we can compute, right? So normally the benefit of doing this is that, so this guy is easy to compute. Okay, but this guy is not so easy to compute. Okay, if we do the other way, hx minus hx given y, then hx is easy to compute, right? Because we know px, right? But the other is not, right? So there's a balance here, right? So in this way, so let's see how we can compute it. So in this case, so this guy is easy to compute. Let's compute this guy first, right? Hy given x. Okay, so one way we can compute that is, so it's the average over both x and y, right? So we can compute the average over y first, and then we do the average over x. So basically, it means that let's say we have p0. So the p0 is a probability that x equal to 0, right? And then we use hy given x equal to 0 plus p1 of hy given x equal to 1. Okay, so now let's see how we can compute it. Yeah, because we know that y equals to x plus z, or x or z, right? Then we can get what? So yeah, let's see. Maybe let's introduce a new notation here. So let's denote this guy as px. Okay, and then the first term p0 is 1 minus px, right? And let's see what is this here, right? So if x is equal to 0, then y will basically equal to what? Z plus 0, right? So it's the entropy of z plus 0, though it's entropy of z. Right? For the other thing is px, and here is the entropy of z times px times the entropy of z plus 1, right? Okay, very good. And then let's see, so here's this plus px. So what is the entropy of z plus 1? So in other words, is the entropy of z plus 1 and entropy of z are the same? Are they? Yeah, they are, right? Because we just add a constant, right? Then the value of the probability does not change, right? Of course, inside and probability of x equal to whatever is changing, right? But the actual probability is not changing. Okay, still have the same probability vector, right? So this equals to the entropy of z, right? Then this is equal to entropy of z. Okay, very good. So we can see that, okay, now we can write c equals to maximum over px. We have hy minus h of z, right? As I said, right, if we do in this way, so the second term, hy given x, is easy to compute, right? But how we can characterize hy? So that is not easy to compute, right? Because hy is a function of px and so on. It's not so easy to compute, okay? But one thing we can actually get here is that, so this guy is less than or equal to, so we know upper bound for y, right? So the upper bound of y is 1, right? So we know this guy will be less than or equal to 1 minus, so this z here is the Bernoulli distribution, right? So we just use the binary entropy function to denote it, okay? And so we know that capacity will be less than or equal to this one, okay? We didn't compute hy yet, right? We just guessed. So this is less than or equal to 1, right? So if it can be equal, then we know this will be the capacity, right? So now the question is that, would that be equal under some distribution of x? Meaning that, so hy has to follow a uniform distribution for some distribution of x, right? Would that be possible? Right, intuitively, maybe let's just try it, right? If we don't have no idea, then let's try maybe, let's say if x is a uniform distribution, then let's see what is the distribution of y. Does that make sense? Let's try uniform distribution. Okay, so now let's write the transition probability matrix as this one. So we use 1 minus p, 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 1 minus p here. Okay, so this basically, let's say here is 0, 1, here is 0 and 1. And this is x, this is y. Okay, so this basically means that given x equals 0, what's the probability y equals 0? Okay, the transition matrix of the BSC, right? We have seen this last time. So if I have that, let's compute. What's the probability that y equals 0? Okay, so the probability of y equals 0 basically means that the probability of y equals 0 given x equals 0 and times the probability that x equals 0, right, which is p0. And plus the probability that y equals 0 given x equal to 1, and then times the probability that x equal to 1, right? And now let's assume it's uniform distribution, right? So basically the first term is 0 and 0, so it's 1 minus p, right, times half, and plus 0, here is 1, 0, so 1, 0 is a p times half, right? What are they equal to? Half, right? So this p times half and this p times half canceled. Okay, and similarly, we can verify that probability that y equals 1 is also half. Okay, you can see that when x is uniform distribution, then y is also uniform distribution, right? If y is a uniform distribution, and then we can see the capacity actually, so this is indeed, so this is the capacity of a BSC channel, right? Is that clear? Okay, great. So yeah, if that's clear, then yeah, let's see another example. The capacity of BEC channel. Yeah, let's see how we can compute it. So basically, the capacity, the BEC channel is given by this, right? From 0 to 0, and 1 to 1. So we have some probability here, 1 minus epsilon, 1 minus epsilon. And then we have a chance that we receive an error here. Okay, and given this, so we can write down the transition probability. So here, the transition probability will now be a matrix. Well, no, sorry, will now be a square matrix, right? So you have here 0, 1, here I have 0, E, 1. So the probability here is 1 minus epsilon, and then epsilon, so let's say here's epsilon, here's epsilon, and 0, And then from 1 to 0 is 0, and epsilon, 1 minus epsilon, right? So this is basically the capacity of BEC, all right? So, sorry, it's not the transition matrix of BEC, right? So now let's compute the capacity. Again, so which is the maximum over Px of mutual information, x given y, okay? So now let's see how we can do this. For this time, so we can use we can expand it in the other way, hx minus hx given y. And let's see how we can do this. Okay, again here, so let's compute this hx given y first. So in this way, computing that is harder, right? So let's see how we can compute in this case. Right, let's see how can we compute it. So the idea is similar to before. So basically, again, we're going to expand it. So basically what we do is that the probability that y equals 0 multiplied by the probability that x given y equals to 0. Okay, and then add the probability that y equals to 1, hx given y equals to 1. Okay, and then we're not done yet. We have another one, probability that y equals to e, hx given y equals to e. Right? Normally, computation of that is not easy, but in this case, it's pretty manageable. Right? So first of all, let's see. So what is the entropy here? So when y is equal to 0, then what is the entropy of x? Right? When y is 0, then do you know x? Yes, you do, right? X is 0. Right? Then there's no uncertainty, so the entropy is 0. Okay? Similarly, when y is 1, the entropy would still be 0. Okay? So we only have one term left. Right? Let's see how we can compute this term, right? So one thing we note here is that the probability that y equal to e basically means that we're making a mistake, right? So this is a probability of error. Okay? And then we times the entropy of y given x, entropy of x given y equals to e. Okay, so in order to evaluate that, we need to compute what is the probability of x and y equals to e, right? We need to compute this conditional probability in order to compute it, right? How can we compute that? Right, normally when we compute conditional distributed probability, we just compute that directly, right? If you cannot compute it directly, then just use the Bayesian rule to see whether we can get something more manageable, right? So here clearly computing that is not easy, right? Given x, computing y is easy, but given y, computing x normally is harder, right? So basically what we use is the Bayesian rule, right? We write the probability of x given y equals to e over the probability of y equal e, right? We write down this Bayesian formula, right? And then normally for the upstairs, we need to expand it, right? In the other way, right? We cannot expand it in the same way, right? So we'll go back, right? So basically, we want to extend it in this way. So px times py equals to e given x divided by py equals to e. Okay? Well, now let's see what does that equal to. Okay? So the magic here is that look at this term and this term. So are there any relationship between these two terms? Right, if you look at this figure over here again, right? So basically, from 0, let's say here, so it doesn't matter whatever x is, right? The probability of this guy would be epsilon, right? That makes sense, right? Therefore, so the condition on x can be dropped, right? These two guys equal. Okay, then they're canceled, right? So then we'll have a px here, right? So given this, then we can compute it, right? So basically, therefore, so this guy will becomes, right, because of this, So this guy becomes P times HX, right? And then we can write down the capacity C equals to max PX HX minus PE HX, right? Before we have HX minus this guy, right? And this guy equals to PE times HX. Okay, and then, so this is max over Px and 1 minus Pe Hx. Okay, and then, so this equals to, well, we can take this 1 minus Pe out, right? 1 minus Pe, and then maximum Px Hx. Right, so can you tell me what that equals to? So can you do that? The maximum entropy, right? What's that? Yeah, the cardinality bound, right? So this guy will be less than or equal to log 2, that will be 1, right? And then it will be achieved when X is a uniform distribution, right? Cardinality bound. Okay, therefore, the capacity of this is nothing but 1 minus PE. All right, PE is basically epsilon, right, or 1 minus epsilon. Okay, and this is achieved when X is uniform in 0 and 1. Okay, then we're done. Okay, so those are the two examples, and so yeah, in the next lecture we're going to see. We may see another example here, and then we're going to see what is the general approach to compute the capacity. So actually, it's not very trivial. But by the way, so let's say, okay, so basically computing the capacity is nothing but maximize this mutual information, right, over Px, right? So we kind of learned that before, if you recall anything, right? So when we learn about mutual information, so we have a very important property of the mutual information, right? So when we talk about the three important metrics, right, is quantity. One is entropy. The second one is relative entropy or KL divergence. Third one is mutual information, right? We analyze so whether it's a convex or concave or whatever in some of its arguments, right? So if you remember, so mutual information is a concave function for Px if Px given y is fixed, or yeah, y given is x given y or y given x is fixed, right? So, but it is so that's a convex function, a concave function in Px, right? And a concave function in Px given y or Py given x, I don't recall, right? So basically in this case, so it's a concave function in Px, right? And it should be Py given x when y given x is fixed, right? Which is exactly our channel, right? So basically we just use convex optimization technique to solve it in general. Okay, yeah. Yeah, that'll be, and we're gonna, so I don't think that was discussed in our textbook, so we may go a bit more details to see how we can do this optimization exactly. Okay, great. Thank you. See you.